welcome everyone. I made this sort of, I brought a bunch of slides. We can work through the slides, of course, but what I just, essentially what I'm here to do for is to tell you a little bit about, well, partly what my research group is doing, and I put that actually more, in the later part of this presentation. And then I want to start out by maybe explaining why, what brought me to doing this research. So I think Pam has organized these presentations over the last few years, and oftentimes people have actually asked exactly these questions, like how did I end up in this specific field? Why did I do this work, like research work at a university in general? These kind of questions. And I think, so I put a bunch of slides for that in the beginning, so that we can start talking about that, and you can interrupt me at any point. You can ask questions at any point. We also don't have to make we don't have to make it through all the slides. I brought way too many intentionally in case there are more questions, but we don't have to go through all the slides at all. And so maybe just to start, so, my group in general, if I have to kind of give you a big picture of what we're doing, is we're looking at these excited electronic states. So we're looking at electronic excitations. Every time you excite an electron in a material or many electrons in a material, we're trying to describe that. And we also look at real-time dynamics, meaning once you create the excitation, then that state that the electron is in is not what we call a ground state, meaning the electron doesn't really want to be there. It wants to go back into its ground state, into its equilibrium, comfortable ground state. And so if you excite it and it's in this non-ground state, then there will be some time dependence that the electron changes its properties over time, essentially trying to make its way back to the ground state. So these kind of things are questions that we're trying to study. I will be, I give you some examples and be more specific of what I exactly mean with these excitations. But the other key point, and you kind of see that here in the background of this photo, is that we're doing the research in my group is entirely computational. So we don't have an actual lab. We just have office space, if you want. And our lab are these supercomputing centers or smaller computing centers. So the photo of my group that we took here, this is in a building here on campus where we have a local computer that has, the numbers change a bit over time, but on the order of a couple of hundred what we call nodes. And each node you can almost think of as a very flat kind of computer that you can, insert them in these kind of huge closets, so to say, right? And so we stick many of them together, we connect them with network, and then we can run our simulations on them. So I'll tell you a bit more why computation itself is interesting, but one of the advantages that we have seen during this COVID crisis is that, in principle, we have no real hold up with our research in the sense that these computers, we always access them remotely. So we never go into this room that you see in the photo to do anything there other than the photo. And so we always work remotely. And so working from home is not a big deal for this type of research as long as we have an internet connection. Now, I said earlier, this is kind of true on paper. The reality is, of course, if you're working from home, you've probably tried this out yourselves. Things are more difficult, right? You've kind of looked up the entire time in your own place. And so those kind of strains, of course, still exist. But at least in terms of, doing our computer experiments, we can still do those from home. Anyway, so let me maybe start by telling you what got me interested in this kind of, maybe in research in general, and then also in this specific line. So these questions, Pam usually sent those in an email. I think this year, Pam, you didn't really do exactly those questions, but since, again, these were things that people asked in previous years, I just left them here and we can use them as discussion starter. So what sparked my interest in science and engineering? So just about my background briefly, I was born and raised in Germany, so I'm German. And as a kid, when it started that we got these shows showed up on TV, and I liked that very much as a kid, right? I know that's very cheesy, but this is really, I guess, how the early things started, like what made me, think about how do things work in very general terms. I had no idea about any specifics, of course, but that got me interested maybe in mathematical subject topics and maybe physics. So I never really did anything outside of school towards that. So I didn't join a physics club or anything like that. But when in school, so in our curriculum, when we go from like, when we go through high school and then the school above that prepares us for university, we can make certain choices. So we have to emphasize certain topics and de-emphasize others. And so at those points, then for instance, I try to focus on physics because I was just interested in it. And the other thing, I would say there were a couple of key experiences that really helped with this stuff. So in the very early days, this is what you can see here. The very, very early days, I was still, this was way before college. I can't quite remember what year it was. Maybe I was like 16 or something. There was a university not too far from my hometown. It was like maybe a 30-minute drive. And they had a chemistry kind of maybe a colloquium series or something. It happened maybe once per month. Saturday morning, school kids from the area could go in and listen to some chemistry lecture geared towards those kids. And the photo that you see here, actually, I remember this is not my photo, so this photo I Googled, but the experiment you can see here, maybe you guys have done yourselves in one of your chemistry classes. What they did is they filled a balloon, like an air balloon, with, well, one with air, one with hydrogen, and one with the perfect mixture of hydrogen and oxygen to react to water. And then they ignited them, right? And I don't know if you've seen this experiment before. Sometimes you see this demonstrated. You see a huge difference, right? The air balloon with air obviously does nothing, right? So then the one with hydrogen, it kind of fizzles and maybe slightly burns, but doesn't really burn. And then the one that's filled with the ideal mixture of hydrogen and oxygen explodes, and not just a little bit. So I think this flame is kind of an understatement. The boom that goes to that room when they ignite this balloon is loud. And so these kind of things, you know, got me interested in this initially. And then what I put here is, so that's kind of still school student times, I would say, pre-college. This is also still pre-college. So the other kind of experience that made a big difference, because I remember it very vividly now. I don't know how much of a difference really it made back in the day, but now if you were to ask me now, you know, that's what I remember what happened. And so this thing here in the middle, you probably have seen the equation before. It's, you know, of course, theory of relativity. And that was also something that happened during, when I was a student still before college. We had to do a mandatory project on some topic, right? So the idea was that people need to learn how to write small reports, and they have to do some research as a student before college. And so they told us we have to pick our own topic and do some research on. And so, of course, I had no idea what I should pick as a topic. And so since I was sort of involved with this chemistry club at that university, I went and talked to some people there. And that was in the physics department at that university. There was a person, Berger was his name. Anyway, he was an employee at that university. And his research topic is theory of relativity, right? And so he said, hey, you know, you could maybe start reading stuff. There are very like nice introductory books. Theory of relativity is super difficult, right? From nowadays point of view, still super difficult. But there are nice introductory books that explain things in a very, maybe initially non-mathematical way. And then also for beginners, there are books that explain the math, I would say slowly, right? So if you want to enter the field, you can start with those books, and you can actually understand it with math that is comprehensible to high school students, right? Which for theory of relativity nowadays, they use math that I have no idea about. But, you know, for the basics, I would say, for getting an idea of what the theory talks about, that is doable with relatively simple math. And so they gave me this literature, they pointed me to what I should read. And so then essentially I did this project. The project in the end was just sort of summarizing what I read. But the key point was, I guess, in the end, when I discussed my report with the person at university, what he said is that he could also see me be, you know, studying physics. And that is something I had never considered up to this point, right? At that point, I was maybe in my second to last year of school before college. And I liked using computers, and I had some basic programming skills. And I thought, well, maybe I should do computer science because I enjoy it. And so then he was really the person who actually made me look into this, what it means to study physics, right? I had never considered this before at all. And so I looked into it. And what in the end attracted me to it was that, you know, the info material that the university provided, they sort of gave a nice picture of what you can do with the research skills that you're learning, which is of course important. And the other thing that actually I think in the end was more important when making the decision is they mentioned in those materials that if you study physics, you learn a lot of basic skills, like some, advanced mathematics, some ways of how you build models. Like, of course, when you do physics, these will be models of, I don't know, a car driving down a plane or something, right? But the skill of making these models, of understanding them, of writing them down in equations, and then maybe use computers to solve them, these skills, that's what the info material emphasized. These skills are needed not just in physics, right? They're not just, you don't have to become, in other words, either a person working in a lab or at a university, and physics will still be useful, because those skills of building a model and using math and computers to solve them, that is needed by insurance companies, by banks, right? It's needed by consultancy companies, because they all require, in the end, you develop some sort of a model, come up with a mathematical description, and then, solve it and predict results from that. And so that really kind of convinced me to do physics, simply because, well, I was 18 at the time. I had no idea what I want to do later. And the fact that you learn something that is super useful, not just for like one particular very narrow path, I think that I found very appealing. And so in the end, I, studied physics at that university. And in the end, I ended up sticking with it and going into research. But at the time, I made the decision that wasn't clear to me at all. All right, and so then you see a couple of well, I would say beach photos. One other thing that made me sort of stay in the field and advance in the field, as opposed to getting a degree in physics and then going off to some other direction and maybe a company or a bank or something, that I had ever naturally really planned for. But what made me stick in science really is, I guess, something that we cannot do right now, which is collaborating and traveling. Well, I guess we still can collaborate, but it's a bit difficult. But traveling both to maybe collaborators, conferences, other universities. So that kind of stuff I started sort of doing in the very early stages as an undergrad. And so you see, some of the locations I've traveled to, and I always enjoyed that, right? Because when you do science and you're at university, you do end up going to visit other places, simply because science really relies on collaborations, on people talking to each other and exchanging ideas. And at least before COVID, and I'm actually pretty optimistic this will also come back once we kind of gotten rid of COVID, that happens by, going to certain places where conferences are and meeting people at those conferences. I always enjoyed that a lot. And so then that's why I put these kind of experiences here. So let me see what I have in the next slide. Oh yeah, okay. I'll come to how I got to this specific position next. All right. So then the other question is, what actually got me into this current position that I'm in? So that was, well, I wouldn't say it's particularly convoluted for a scientific path, but at least it involved several steps. And so I initially started out at this university. That's the place close to my hometown, like 30 minutes away from where my parents live. It's a technical university, and I did my first, I think, 3 years there, which worked great. Was in the physics program, and at the time in Germany, the degrees were not based on bachelor and master and PhD, but they had a different scheme where you get your first degree after 5 years of studying physics, as opposed to the bachelor degree, which is I think 4 years here. And so the first 3 years of those 5 years I did at this university. And then, so the university was great and the teaching was also great. After a couple of years, the stuff that you do in your physics curriculum shifts to be more research intensive. And the department of physics at that university was a lot smaller than in many other places in Germany. And so when it came to the research oriented work, as a student, then maybe 2 of my friends and myself, we decided to go to a different place, maybe an hour away from there, or maybe 90 minutes, I don't quite remember, but it's not so far, which is this university here in Jena, which is where I finished my degree and also stayed for my PhD. So I did both of these degrees here. And this little detour here is, as you can see, during my time as a PhD student, I went to Santa Barbara for a project where I did research with a professor at the university there. So this was something my boss at the time here in Germany came up with this idea, right, as a collaboration, and it initially was conceived by my boss then. And so I was the student who got to go and work in this group at UCSB, which I really enjoyed. This was my first visit to the US ever, right? So I never had been to the US before, and I was there for, I think it was maybe a total of about 3.5 months during my PhD time. So I did that research project, was super helpful, again, to figure out what I wanted to do later on, in the sense that, you know, you do your PhD in a group and you know a lot about the activities in that group. But if you have a chance to see some other environment during that time, it's super helpful, because it helps you to get an idea what else is there, what do other people do, how is research done at another either university or another research group. So these kind of experiences, I think, are super helpful. And even nowadays in my own group here, I try to encourage my students to use maybe 1 or maybe even 2, if need be, summers of their PhD time and try to get that experience. And so there are various ways of doing that. You can, for instance, go to, I think that's, sorry, this participant window is kind of in the way here. Let me see if I can close that. Apparently not. Okay. Well, one of the things that you see at the bottom here is this, is Lawrence Livermore National Lab. So in other words, the national labs here in the US give you the opportunity to spend the summer there and do summer programs. So they have that, I think some of them have this for undergrads. The majority is probably for graduate students, but doing these kind of things, I think, are super helpful. Like maybe 3-month stay at another place just to see what's going on there, both scientifically and culturally and everything. I think it's very helpful. Anyway, so I did that at UCSB, had a great time, went back to Germany to finish my degree because I didn't have my PhD at the time yet. And after that, you know, after having been to the US and seen how things work there, I wanted to go back and do a postdoc. So that would be the next step after PhD if you're trying to stay in science. So in other words, you get your PhD, that's a degree. And then everything after that are essentially just jobs, if you want to call it that. So there are no further degrees that you get. But if you want to stay in science and in academic research in your future, the next pretty typical step, maybe not mandatory, but pretty typical, is doing this postdoc, which is essentially a research position at another place, and usually it's not a permanent position. And so that was also the case for this position here at Lawrence Livermore National Lab in Livermore, which is maybe an hour. There's a chat message here. Hold on a second. Chat. All right, no questions yet. Okay, well, I'll keep the chat window open in case something comes up. Yeah, so Lawrence Livermore is a national lab, maybe an hour south of Berkeley in Livermore. And, you know, so I did research there for about, let me think, I think it was almost 3 years, which is pretty typical for these postdoc positions. So these postdoc positions can last anywhere from, I would say, 1 year to 3, 4, 5, 4 years maybe. It depends a bit on the details. In Livermore, what they do is, if you get there, they usually hire you for initial 2 years, and then it can be an additional 1 year at the place. And then usually, again, it's not a fully hard cutoff, but usually they want you to then either move on to another position somewhere else, or that you get converted to a staff scientist at the lab. So both options exist. Yeah, so after my PhD, I did that. And the other thing I should also emphasize, because that's a question that I oftentimes have gotten in the past, is you know, if you get your undergrad degree, like maybe a bachelor or a master's, if you get that degree, why would you want to continue to do a PhD? That's a very good question. In the end, you have to decide all this for yourselves, but that maybe there were 2 things that convinced me of doing it. Number one was right after I joined my undergrad institute, maybe during the introductory week of my undergrad time. What some of the people there told us is that out of the people who finished their physics undergrad, about 75% will move on to do a PhD. So that seems to be, I don't know if this is a peculiarity of that university or of physics. I'm not 100% sure because I never really compared this number later on, but essentially at that point, it seemed like a large fraction of the people is doing it. So then I started playing with that thought myself, right? I thought like, well, you know, if 75% are doing it, it seems to be not such a crazy thing to do. And the other thing is, if you're in a PhD position, certainly in any of this, either engineering or sciences, those positions are not, you shouldn't think of those as school as much, right? Because first of all, you're paid, right? So you're not paying tuition or anything like that. You get a salary, which is maybe not, you know, the best salary in the world, but it's, you know, reliable salary. And the other thing is, it's not, I know it's called grad school, especially here. I think it's not really called that in Germany, but in any case, don't think of this as school, right? What you're really doing is, especially in physics and material science, so my home department is material science. What you're really doing is research. So you're going into the lab every day and you research things, meaning you use the skills that you learned, maybe as an undergrad, maybe in your first year and second year PhD, you use those skills to do things that have not been done before, right? So in other words, this is really not school in that sense, even though you're learning things, and I think that's why it's called that. And maybe in your first year, you have to take a bunch of classes. That fraction of your time is actually very small. So you're not taking a ton of classes while you're doing a PhD. It's mostly research work. And if you enjoy that, then a PhD is maybe the thing you should consider, because it is also just fun. In addition, of course, it does prepare you for certain positions, right? So meaning for certain jobs in industry. So certain companies, especially if you want to get, you know, if you want to climb their hierarchy, they at some point likely require a PhD, especially bigger companies with like a formalized HR department and everything like that. Oftentimes they have certain kind of lists of requirements. And, you know, if you have a PhD, you can advance beyond a certain point, and if not, then not. Certainly in academia, if you want to, you know, stay in academia and do research, and then maybe you do this postdoc and this kind of things, for that you also need a PhD. And so if you enjoy research, I think a PhD is not a bad thing to do. And so, yeah, that's, I guess, how this decision happened for me. I don't know if, yeah, I don't think of this as I made all these decisions as an undergrad student. That's absolutely not the case, right? So that was a lot of randomness, both in terms of the research topic I ended up doing. So this kind of happened at the transition here, when I went from, you know, after 3 years, I went to the second university here in Jena, when essentially I've talked to like a friend at this university. Like, he was a staff scientist at that university, and he recommended me, hey, you should look into this person's research. That could be something that you may like, because if you're, you know, you like computers and everything. And so this is how I found that particular professor. So there were a lot of places where a lot of randomness happened, but I guess that's just how it is. Okay, so then, yeah, I did my postdoc at Lawrence Livermore. And after that, I think the slide has no follow-up here, right? Yeah, exactly. After that, I applied again for positions, because the postdoc, like I said, ends after like a maximum of 3 years. So you have to either apply for staff scientist or you know, either another postdoc or faculty positions. And I tried to apply for faculty positions, and it worked out actually here at the university. So that of course was a huge opportunity, right? So that was what I wanted to do at that point in time. I didn't know this coming in. And when we moved from Germany to the Bay Area, where Lawrence Livermore is, at that point, I had not made up my mind at all if I want to stay in academia and you know, become a professor and all this kind of stuff. Was not clear at the time. But then, you know, at the point when I applied and then I got the position, at that point, this was my preferred route. At the same time, I should also say, if you go through this whole thing in terms of undergrad, PhD, postdoc, so I would say all of you guys, you know, have to have the capabilities to do a PhD if you want to, right? A PhD, I'm not saying everyone who tries will get one. That's not how it is. But a PhD, you know, you will, if you do a good job as an undergrad and you get a good GPA, you will find a PhD position that lets you in, most likely. And you can then, with, again, hard work, that's clear. You will have to put in a lot of work. But if you do that, it's very rare that a person, you know, that does put in the work and that does research and talks to their, you know, to their colleagues and to their advisor and everything, that they then will not get a PhD, because not because it's so easy, but because, you know, you have maybe 5 years to do the PhD, and it's very rare that you're so off track that that you will not end up getting one. You need to make sure that you search out people that you can talk to, right? And if you get stuck, it can certainly happen that you get stuck scientifically, and maybe there's nobody immediately there that can help you. Those situations happen. And in that case, it's important that you then search out people to figure out how to continue. But a PhD is very different from an undergrad, right? It's really, you spend a lot of time in it, you do research work, and then if you search, either if you have or search out the support infrastructure in terms of mentors and advisors and everything, then you will be able to get a PhD. So I was lucky that my advisor was very caring, right? Meaning he was there. He had like this open door policy, right? You could, if he was around and not on travel, you could literally just knock on his office door and he would chat with you if you had questions. That is, of course, not the same everywhere, right? You may have a situation that's more difficult, but you know, in all the universities and places that I've seen so far, even if your PhD advisor may neglect you sometimes, you have support networks, and if you make use of them, you will get a PhD. And with a postdoc, it's sort of similar. If you haven't lost interest in research yet, chances are that you find a postdoc position. Meaning, you know, there are certainly openings over and over again, and you know, if you do a good job as a PhD, if you publish a couple of papers as a PhD student, you will then be recognized in the community, and then you can most likely find a postdoc position. Of course, it's always helpful if you have an advisor that supports you, right? That's clear. I was lucky with that, I have to say. And you know, that's probably early for you guys now, but if you end up being in a situation where you don't have that, make sure you either push your advisor or search out additional mentors, right? Anyway, so then the real hard cut comes, I think, going from postdoc to faculty. I think that is oftentimes, there's a large, I wouldn't even call it down selection, but there is a large, I think that's the number of postdocs that are looking for faculty jobs and the number of jobs that are available is very different, right? You have a large number of postdocs looking and not so many faculty positions. At the same time, you guys are undergrads. That shouldn't scare you off right now at all, right? This stuff develops, this stuff changes over time, your interests change over time. If you like research, stick with it as long as you can. And if at the end of a postdoc you find, okay, I've applied for 2 years, I didn't find a faculty position, okay, then you find a position in industry. At that point, you're not too old, you got a lot of good skills that help you in industry, and you got a PhD. So I think that's not a terrible situation to be in either. So don't be too scared to just jump in. What made me in the end stick with computational research, and why do I like doing this kind of research? Well, it's really the freedom that I have here to pick whatever I want to do. Now, when I say what I want to do, that doesn't mean, okay, today I want to go biking and tomorrow I want to do bungee jumping. It's more the research topic that I want to focus on. I can now more or less determine myself. Not completely, in the sense that I'm still sort of, I want to hire students like you guys and then pay them as grad students. And so for that, I have to get money from national funding sources like the National Science Foundation or Department of Energy or the Office of Naval Research. So certain, places that provide research funding. And what the process is, I have to write a grant where I describe what I want to do, why it's interesting, how I want to do it. And then I send them this grant. And if they review it well, then I may get the money from them to actually do that research. So the money will then go, for instance, in my case, and pay, a research assistant their salary, essentially. So I have to do that. But other than that, I can more or less research whatever I want to, as long as it, fulfills these criteria, as long as it's interesting and answers a question that helps, that helps either fundamental science or maybe society with figuring out a problem that needs to be figured out. And so I have maybe 2 pictures here. One of the things, you'll see that on the next slide, one of the things we're doing is looking at optical properties of materials, so we can really explain why does a material look a certain way. And so what you see here is actually not a photo, it's a computer generated image. And so the example I always like to give is these couple of objects here at the top. This shows results that we produced using our numerical simulations. So what you see here, these objects are all titanium oxide, TiO2, titanium dioxide. And the difference between the different objects here is the amount of sulfur that got incorporated into the material. So people, in other words, put sulfur into TiO2 to make it absorb more visible light. And you can see that effect, right? So this one here, this sphere is very transparent because it has no sulfur in it. And then the more sulfur you put, the more brown the material looks. What that means is the more light it has absorbed, right? So it's certain amount of light were absorbed. And so understanding these kind of things is something, for instance, that our simulations can do. Now you guys are here for the MRSEC, and so one of the research in my group that we are doing there is this. Again, this is also, of course, a rendering of a scene. But what we're looking at for this MRSEC research is how does light, again, so the light is kind of symbolized here with this spiral, interact with the magnetic moment of the material. So you can see this little black arrow here, and this green area is supposed to indicate that this black arrow is actually, you know, rotating, if you want. And so the light, when it comes in, the reason I put it here as a spiral is, so that you guys may know light can be polarized. And the question that we're trying to answer for the MRSEC is, for instance, how does circularly polarized light interact with these processing magnetic moments? Anyway, so that's some of the calculations that we're doing. And then, you know, one advantage here at Illinois is that we have very nice computing resources. So this building here is actually on campus. That is the petascale computing facility, and that has one of the computers that is in this facility is this Blue Water supercomputer, which is one of the machines that we're using. The other thing that's really great about Illinois is, and that's kind of shown in this picture up here, is that we find very good collaborators very easily. So people are very collaborative. And for us as simulation people, we always want experiments to compare with. And so finding that has turned out to be very, very easy here at Illinois. We find people who are doing experiments, you know, using cutting edge facilities and techniques. And so we can compare our predictions from the computer simulation to their experimental measurements. That's actually a huge plus. And then of course, you know, great students. You can see my group picture over here. So this is sort of a figure that shows you the, you know, the length scale certainly on the x-axis and sort of like a application scale on the y-axis of what can be done with computers in material science, for instance. And as you can see, this happens across all sort of length scales, and the methods vary wildly as you go across those length scales, right? So you use completely different things to describe macroscopic objects with a computer, which you completely do, right? Like for instance, this is sort of it's maybe a finite element simulation of, you know, the forces acting on a bolt or something like that. But if you go to on a different and want to describe things on a different length scale, you use completely different methods. And so what's the most, I guess I'll just keep it at that. What we're doing in my group is, so if you've heard of molecular dynamics before, maybe in a class or from somebody that you talk to, molecular dynamics happens sort of at an atomistic length scale. So in a molecular dynamics simulation, people have individual atoms, usually a lot of them, meaning maybe millions, or I think maybe the largest simulations in molecular dynamics are maybe even billions of atoms, but the entity in your simulation is individual atoms, and you trace their behavior as a function of time. So that's sort of the upper length scale for my group. We're closer to maybe here, right? So we're certainly looking at electrons. Molecular dynamics normally does not really include electrons explicitly, and we do include electrons. And so what that means in practice is we have to use slightly different methods than what molecular dynamics is, which then leads to the computational cost being so high that we cannot look at millions of atoms. But in our case, we're typically looking at something between, I say between 1 and 1,000 atoms. So it depends on the exact question that we're trying to ask, but that's sort of an order of magnitude or a range of order of magnitudes of numbers of atoms that we can study, including their electrons. So that's sort of where this work is. And maybe before we completely run out of time, I will show you at least one last slide. So this is sort of an overview of what we're really doing. So I think let me just try to move this participant window again. You guys don't see these windows in your case, right? It's just on my screen. Okay. So usually, so when I say excitations, right? What does excitation mean? So if you're looking at a material in its ground state, you do have these atoms sitting somewhere, right? So this would, I don't know, this is for instance, I don't know, aluminum or something, depends on what you want to look at, silicon, some atoms sitting somewhere. And then you can see these red and blue kind of structures here. These are isosurfaces that represent the probability of finding electrons. So this is, I'm not, you know, you don't look at this figure and say, oh, I see this is what the electron is doing. That's not how it works. This is just a visualization, but the simulation deals with these probabilities. So we predict where is the electron very likely to be, where is it not likely to be, and these kind of things. So that's true in the ground state. And then you come in with a process that excites this ground state. And so excitations that we're studying in my group are either you know, light excitations, can be sunlight or laser light, some optical process, or it can be particle radiation, meaning we are shooting a proton into a material or a charged ion. It doesn't have to be a proton, could be, I don't know, a silicon ion or something. So just to show you this what that looks like. Let me see if I can actually go back here. Yes, this one. So if you look at this simulation down here, this will be a movie in a second. So you can see this is for aluminum. All these dots here are aluminum atoms. And then we're shooting a proton into the material. And you can, sorry, how do I do this actually? The shooting process here. Oh, of course I can now not play this movie. I'm sorry. I think it played earlier, right? And this just stopped. Oh, here it is. Okay, so here's the proton, right? The proton flies into the aluminum, and these oscillations and this color stuff that's happening here, this is electrons reacting to the fact that a proton is coming in at very high velocity and, you know, depositing energy into the electronic system. So this is sort of the time and length scale that we're looking at, right? We're looking at, you know, maybe a couple of hundred of atoms and the associated electrons and what they do as a function of time. So this was one of the simulations by Alina Kononov. So she's one of my students who just defended their PhD actually. Okay, so this is the type of excitation. And then, so we're trying to study that. We're trying to look at how does a material respond to the, if you expose it to light or to particle radiation. And then the thing that you've seen on the previous slide with this movie sort of is, this stuff is, as I said earlier, time dependent, meaning, you know, you start at t equals 0, time 0 in the ground state. And let's say you then come in with your laser pulse, you excite the electrons, and then you measure the properties of this material after maybe 1 femtosecond, 2 femtoseconds, 3 femtoseconds, and so on. And so that makes this whole thing, this is what kind of schematically shown here. This makes this thing dynamical, meaning the electrons change as a function of time simply because they're in an excited state and they want to evolve away from that. And so that is something that people can measure in experiment now. So there are, you know, national labs like, for instance, SLAC in Stanford. They do ultra fast experiments, meaning experiments on a femtosecond timescale, maybe even faster nowadays. And so they probe materials at those timescales. And in my group, we're trying to provide simulations of materials on those timescales. And then the last thing, let me see if I can get this window moved also. Okay, not quite. Here it is. The last thing that we're now trying to do is, in the end, we're material scientists now. And so we want to study, we want to be able to say, okay, why does a certain material work very well or why does it not work well? So that's kind of what these first two things are doing. Ideally, in material science, we are able to find better materials for a certain application, or maybe even the best material for a certain application, but we want to make, you know, we want to make new materials, or we want to improve a material's property. And so this is what I put here as materials design. That is actually very difficult because the two techniques that these two topics here on the left-hand side, each individually takes a huge amount of computer time for a given material. Like, let's say we want to look at, I don't know, zinc oxide really in detail. We can do that, but doing that for 10,000 materials and then pick the best one, that is either impossible or extremely slow. And so we typically don't do that. What we try to use is for that part of the research where we try to find maybe the best material is computational or experimental databases, which is a situation where people have either done a simulation or an experiment. They make, nowadays, people started making this data available to everybody, right? So they put this stuff on the internet in big centralized data repositories. And you as a student can go in and say, okay, I don't want to redo that same simulation because person X already has done it. The output is here. I can just use that. And, you know, if I have output for 10,000 materials, then I can start analyzing that output and looking for things that maybe the person who provided the output in the first place either didn't think about or were not interested in, right? But that hasn't been done before. So that is now something that we started doing to some extent. I would say both in my group and also here at the university more generally. So there are teams that are now forming that bring together material scientists and data scientists, because in order to either create or use such a database, the problem is that in material science, we oftentimes don't have the training to really analyze large amounts of data very quickly. And so we're trying to train now students at the, at the intersection of these two fields. But this is kind of the big picture. And so applications of the work that we're doing is, one is clearly photovoltaic materials. I think I have a couple of examples on the next slides. I don't know how much more time I have here, 3 minutes, I guess. This is an example for bioimaging, where people want to understand the optical properties of these semiconductor nanocrystals here, put them potentially into cells and detect from the optical response whether the cell has cancer or not. So this, again, it goes back to the optical properties ultimately, and that's what we're trying to understand. We're very far from cancer research in my group, but understanding optical properties of semiconductor materials is something that we can do, and that we've done here, for instance. The radiation damage part, I'll just show you this one introductory slide here, is something that we hope that can be used to manipulate materials. So if you have a certain material with a certain defect in it, for instance, is it possible to use this incoming radiation beam of protons maybe to either heal the defect or make it worse, depending on what you want to do to the material? So can we manipulate the material with the radiation beam? And to understand that, we're trying to do those kind of simulations. And the last example, then I'll stop for questions, is this example here where we used a database. I think, let me see, are these references on these slides? I think there are, right? No, of course not. Send me an email if you want to see some of these papers. They're also on our website. But the question that we try to answer here is, if you want to have, let's say you come up with a new solar cell material, which is the absorber, right? You put it into the sunlight, it absorbs material, sunlight very nicely. What you still oftentimes need to do is you need to get the electrons and holes that the light creates out of the material. So that's what we call a semiconductor heterojunction. So we're trying to come up with another semiconductor that is a good electron transport layer, which is this ETL here, and another semiconductor which is a good hole transport layer to actually get the electrons and holes out, to actually then drive current through an electrical circuit to charge your phone or something. So in other words, if you come up with a new solar cell material, sometimes it's not clear what to use as these electron and hole transport layers. And so in this example, we used the database to quickly screen a large amount of semiconductor candidate materials from a database. We didn't build the database. That's something that was online already. And we just went essentially through the database to find potential candidates. So that's some of the examples that we're trying to research. In addition to very fundamental questions like, after you excite the electrons, how does it actually dissipate this excitation energy? And these kind of things are also, I wouldn't say not understood, but more research is needed, and we're trying to also contribute to these kind of fundamental questions. Good, that's a good question. So I think so certainly you're right that we and also I started as an assistant professor, and I'm still an assistant professor, right, at least on paper. What happens is you start an assistant professor, which is, you can maybe think of this as sort of a 5-year position. Certainly here at university, it's sort of like a 5-year period. And during that period, you're supposed to establish your research program, right? Your research portfolio with a bunch of projects, a bunch of papers, maybe some grants. And at the end of those 5 years, you're evaluated, meaning you put together everything you did. And I'm putting quotes here because, that's of course a difficult thing to do, but you kind of, you prepare a package that summarizes what you did, and you submit that to the university, and they put you up for either do or don't put you up for promotion, which means you then become a tenured associate professor, which is not full yet, but that's associate at that same university. And then you have another couple of years. Again, you do, you build your reputation, and you do better work essentially. And then you can be promoted again to become a full professor. Alternatively, some people also, either during their first 5 years, we use that like 4 years, for instance, either that, or at the end of their 5 years, go to another university. That could happen, right? Sometimes you find a better match somewhere else. You can certainly apply and go there if you want to. And the other solution is, if you do not get promoted at the university that you went to, you can then also go to another university and try to get a position there. So all of these routes exist. Yeah, but you don't have to leave if you don't want to. If you find a better match, like research-wise, I know that sounds very abstract, but it doesn't. The environment does matter, right? So it's not that each research can be done anywhere or everywhere. Some research benefits from having a certain environment, and if during those 5 years you notice, it's a better fit at that other university, well, then I guess it's in your best interest to go there. But it's certainly not so that the university here says, hey, after like 5 years you need to leave. That's usually not what happens. I think either way is fine, right? If you enjoy physics, I think there's nothing wrong with sticking with physics. And for instance, my PhD was still in physics. Yet again, during your PhD, you apply your skills to a certain problem. And even during my PhD, that was actually, we did apply this to certain materials, right? So there's a lot of crossover between the fields and everything. you know, if you like physics, I don't see a reason why not sticking with it. I think you can later on, you know, still transition to material science if you want to, especially if you do some condensed matter physics postdoc, a PhD program, that prepares you very well to do material science after, right? So it's, you learn the foundational physics that you need to describe materials. I think that's perfectly fine. At the same time, if you do already know you want to do materials research as quickly as possible, there's nothing wrong with going into materials science. I know this is a very vague answer. Don't see this as a defensive answer. I think it's just, it depends very much on your preferences and also the place that you go to. So in certain places, people that do this exact same research that we're doing are in physics departments, and in other places, they are in materials departments. So it's really not so, you know, so that's a clear-cut answer, I think. I would say that depends on what you do during your break. Now, let me give you two examples. One type of break that I've seen people doing is something like a work and travel program, right? So let's say they did physics for 5 years. They didn't want to see anything to do with physics for a year. And in Europe, I've seen a couple of people, they went to Australia and picked oranges for a year and did work and travel. They loved it. And then you can go back into science and then you do a PhD. I think that's nothing against that at all, right? And the second route that I'll tell you now, I also have nothing against it. The only downside is it will be much more difficult to go back to a PhD. And the second route I'm having in mind here is if you go to your undergrad degree and then go to industry and work for a year, presumably sort of close to what your degree equipped you for, right? So let's say you work in some, let's say, I don't know, scientific company or in a consultant company, you get trained there to do work for them. The problem why you will likely not go back to do a PhD is once you work for a company, you get salary. And once you get a salary, you get used to it. Meaning, you know, maybe you buy a car, maybe you buy a house, or you move somewhere else, or you make adjustments and sometimes commitments, and a company most likely pays you a better salary off the bat than a PhD program will. And so in other words, if you do that for 1 or 2 years, and then you go back to do a PhD, very few people are willing to take that salary cut. I know that sounds very trivial or very like, you know, boring as a reason, but I think it's very difficult. It's not impossible. Nobody will hold you back from doing it, right? If your job in that company is giving you skills that you want, and then you apply into a PhD program, chances are you get in, right? But I think it will be, you will lose motivation, I think, right? Because it's not that these jobs in companies are terrible, not at all, right? I mean, presumably you get your undergrad, you go and get a job that you like, and then you have to give all that up. And, you know, that again, if you do it, totally fine and nothing against it. But I think the likelihood goes down that you will make that step, I would say. In the end, it's up to you, right? I think that there's nothing wrong with it and there's no like rules against it. But it may be more difficult to actually do it. So that's a good question. I think typically departments publish these numbers on their websites. I think in our department, it's about maybe 5 years, something like 5 years, maybe just above 5 years. So it's clearly a time commitment, right? And certainly, I would also maybe say another thing. If you don't like the research work, just doing the PhD to get a PhD, I don't know, that's probably not worth it. It's probably not worth it in terms of pain that you will go through, right? Because you will have to do research if you don't like it. It will be annoying every day. And it may also not be worth financially because chances are you earn more once you have a PhD and go into a company, but there is a 5-year delay. Not that, you know, like if you go into a big company right after undergrad, you will still be promoted during those 5 years. And so if you add up all the numbers, I don't know if like the pure net value of a PhD is actually a win or not. But at the same time, you know, if you really like the research work and maybe you want to become, you know, maybe a group leader in a company or at university or sort of like a manager, chances are the PhD will help you a lot, right? And the other way around, chances are you may not be able to easily do that without the PhD. Now, these formal criteria, like I said, I don't think there is any law that gives those formal criteria. It's just oftentimes big companies where they have research groups maybe and like sort of a hierarchy, they oftentimes have a formalized HR process. And so then there are these criteria. if you go and start a startup, then you can do whatever you want, right? You can do research, you don't need a PhD, you can, so it depends a bit on the details, I would say. But overall, a PhD, I think, takes about a bit above 5 years, I think. This is unbelievably rare, right? So chances are that does not happen to you. Really, you can take my word for this. I'm not just, you know, making numbers look pretty. It's super rare that that happens. And often, and it's also not like, again, don't think of this school that you go in, you do this for 5 years, and then you fail. This is also not how it works, right? I'm meeting my PhD students once per week, individually, we discuss progress. So if something were to go wrong, in quotes, this is caught early on and fixed early on, right? Meaning if the project doesn't work out for the student, we change direction. If the student needs help to understand a certain research method, we get them there. They have, you know, we talk to the student, the other group members talk to the student. So it's super rare that you will do this for a couple of years and then just end up with no PhD. Again, don't make this your main concern because it's absolutely unlikely. Again, I'm not saying it cannot happen, but certainly unlikely. Oftentimes so one of the options that you would have is, and that's usually what I have seen, if people don't want to continue, maybe after 2 years of their PhD, they notice, okay, this is really not for me, I want to leave now. Oftentimes, since you have already done 2 years worth of research, you can get a master's degree. And that's usually what happens, right? So, you know, you would talk to your advisor, again, hopefully not the first time after 2 years, you would talk to your advisor, and then guys can agree that maybe a master's degree is better for you. And then you can leave with a master's degree, which is still a graduate level degree. It's not a PhD, but it's a graduate degree. Okay, and then what's the other question? If you went straight into PhD, can you use the work you've done to get your master's degree? Yes, exactly. No, you would not have to start from scratch. Yeah, you can definitely use that work and get a master's degree. I would say it's a mixture of both. So it's definitely advisable once you get your PhD in a very narrow field, right? I know this sounds like computational materials, but that's a huge field. My PhD is actually much more focused on like a project with certain methods and everything. And it's usually very advisable doing a postdoc to stay in the bigger kind of field, like for instance, staying in computation, or if you were to, let's say your PhD research is on solar cells and you did computational work, you could then stay in solar cells but do experiments. So it's helpful to deviate, but not too much. So for instance, I think it's very difficult if you did materials research for your PhD and then you do astrophysics or something, simply because that's a huge, you don't really can transfer that much, right? Some skills you probably can still transfer, but not that much. So especially if you want to do academic work after, at the time you apply for a faculty position, you want to tell the places you get interviews at somewhat of a coherent story what your group will be doing. And you can do that either by saying, okay, in my PhD, I learned these methods and learned that. And then in my postdoc research time, I learned new methods that complement these other methods. And now I can do this other stuff. And overall, my group will be doing this. Or alternatively, you can say, in my PhD, I did computational work on solar cells. Now I did experimental work on solar cells. And my group here will be on solar cells, and we will cover both computation and experiment, for instance. So there is no really fully pre-described path, but it's good if you can sort of if you can diversify when you do a postdoc, and yet when you present this to a hiring committee after, you can sort of sell it as a coherent story. I think that's maybe the way to think about it. Oftentimes what happens is when a student comes in, and we already have funding for a certain project. What that meant is we had to write a proposal early on, submitted that, and in that case, so we have to propose something specific, right, to that funding agency. And then when the student comes in and that student is interested in working on that project, they start out with that project. Usually, but don't think of this as this funding project and the thesis have to be matched up. Oftentimes what happens is a student starts on a certain project, works for maybe 1 to 3 years on that project, and then that funding source either ends or changes. That's not a problem, because what we then do, and that's essentially my job, is to make sure that the follow-up funding source is aligned with what the student did before, such that the overall thing after 5 years can become a PhD thesis, like sort of a coherent PhD thesis. So even for instance, if in the first 2 years you work on, I don't know, oxides, and in the next 2 years of your project, you work on on halides, or I don't know, I'm just making up stuff now, but on some other group of materials, it still is such that the thing that that will be your thesis will be overall a coherent thing, even if your funding source and your specifics change. Now, the other thing you asked about whether whether I'm dictating the project or if the student can have input. So it's absolutely the student should have input. Ideally, what works really well is if we start out with a certain project and the student starts out just because they have to kind of become familiar with what is, what methods are we using, how does the theory work, how does the computer work, and all this stuff. But as soon as they have those skills and they can take that and do their own stuff, it's great if the students come up with their own, own directions, own suggestions on where to take this project. So even if a funding agency funds a certain piece of research, it's rarely such that it's completely dictated that each step over the course of 3 years is completely predetermined. So first of all, that's not how we write the grants, but even from what we write into the grant, you can easily deviate simply because, let's say in year 1, you find result X, and that is unexpected, right? Then you cannot simply say, okay, I'm going to crank year 2 and 3 just the way it was proposed. You make then adjustments. And so that's exactly when student input is important and crucial. Thanks for coming. Stick with it. It's worth it in the end.